Hey guys, it's Dr. McJunkin. Welcome to week 3 of virtual learning. Time flies. We're going to get into looking at lesson 5 today. We're going to look at derivative applications. What does that mean? So we're going to be reviewing absolute and local extrema, absolute local max, mins, increasing, decreasing, etc. We'll also be looking at concavity and second derivatives and the second derivative test. So I've got quite a bit of review material up here at the top that I'll go through pretty quickly, but feel free to pause the video and write all this stuff down if you need to review. So a function f has a local maximum when its derivative equals 0, so it looks like a horizontal tangent line, and where the derivative changes from positive to negative, which means the function changes from increasing to decreasing. Because remember that a positive derivative means I have a positive slope, which means I'm increasing. A negative derivative means I have a negative slope in my original function, which means I'm decreasing. The opposite for the local minimum, you still look for where you have a derivative of 0, where you have a horizontal tangent line. And then you want the derivative or the slope to change from negative to positive, because you want your function to go from decreasing to increasing. And a function can have absolute extrema as well at the highest and lowest points on a given interval. So this one has to really happen on an interval. They have to give you an interval A, B to check. This can occur either at critical values. Critical values are where your derivative equals 0. So what we were doing before to find the critical values helps us find local max and mins. So your absolute max and mins can happen at critical values where your local max and mins happen, or they can also happen at the endpoints themselves. So you have to test all of them. We'll have an example of that as well. Let's see some examples of what this is going to look like. Let's look at graphs, algebraic, and absolute stuff. So we have to be careful when looking at graphs to know exactly what the graph is showing us. It tells us this is the graph of f prime. This is the graph of the derivative, not the actual function. So this is the graph of the derivative. At what x values does the actual function f have a relative min? And I want to explain my reasoning. You might say, hey, look, here's the minimum. I found it. Here's my relative minimum. That's the relative minimum of the derivative. This is the graph of the derivative, not the graph of the function. So I have to go back and see, what am I looking for if I'm wanting a minimum? My second point says I get a minimum when my derivative is 0, so I have a horizontal tangent line, and where f prime changes from negative to positive. So where do I have f prime being 0? If this is the graph of my derivative, my function is 0 at 3 different places. At these 3 places, that's where f prime of x equals 0, because it's crossing the x-axis, its y value is 0. Yeah, so I'm not looking for these points here where I have horizontal tangent lines, because looking at my derivative, I want the derivative to be 0. That means crossing the x-axis. Now I want it to change from decreasing to increasing, or in this, because I'm looking at the derivative, I want it to change from negative to positive. So I want to change from negative to positive. So negative values of my derivative means I'm below the x-axis. I'm negative here. My function is below the x-axis, so my f prime value is negative. Up here, my f prime values are positive because I'm above the x-axis, and at here, right where they cross, they're at 0. So right away, I can say at x equals negative 2, there is a relative min. So x equals negative 2 is a relative min of f of x, because f prime of x changes from negative to positive. So I know this looks weird that this is the minimum, but it is, because I'm looking at a graph of the derivative. Let me go ahead and move this up so you can see better. X equals negative 2 is a relative minimum of my function. There's one more. Pause the video and see if you can find it. Okay, hopefully you pause the video for a second. The other relative minimum should be here, where I'm going from negative to positive. So x equals 3 should also be another relative minimum. Let me see if I can make this a little bit brighter for us. Yeah, a little bit better. Okay, so x equals 3 is also a relative minimum. So I would also copy this statement again so I can prove that I have a relative minimum. In case you're wondering, this other point, this is a relative max. We weren't asked to find it, but you should be able to prove to yourself that that is a relative max. Let's go ahead and move this off the screen so you can see a little better. Okay, so you should be able to prove that's a relative max because you're changing from positive to negative at that point. Okay, well, let's look algebraically instead of graphically here. So I've got a differentiable function where the derivative, again, they're giving me the derivative, not the function. The derivative equals this whole crazy thing. At what x values does the function itself, f of x, have a relative maximum? So again, for relative maximums, like we saw up here, the one that we weren't asked to find, but we could see, I'm looking for when my derivative changes from positive to negative. Okay. So I want to first set up and find my critical points and say that I want my derivative to be equal to 0. So 3x minus 2 squared times x plus 1 times x plus 4 should be 0. So I want to find all the different possible extrema or critical points here. So my critical points, or where I could find extrema, are going to be at x equals positive 2, negative 1, and negative 4 from each of these pieces here. So I've got something going on at each of these places, positive 2, negative 1, and positive 4. And so I'm going to go ahead and draw myself a number line of f prime. And I'm going to put my zeros on it. I've got negative 4, not to scale, negative 1, and positive 2. Okay, so now I want to test to see what's going on in between all these. Is my derivative positive or negative? So find some test values. So in this first region, less than negative 4, I can plug in negative 5 into my derivative, so I'm going to add that prime there, into my derivative, and I get 588. So I'm going to put a little positive here. My derivative is positive in that region from negative infinity to negative 4. If I choose negative 2, which is in between negative 4 and negative 1, I get negative 96, which means I've got a negative value for my derivative here. If I plug in 0 to my derivative, which is in between negative 1 and 2, I get 48, so I'm positive here. And if I plug in anything above 2, I'm going to be boring and do 3, I get 84, so I'm also positive here. Okay, so let's see what this means then. So in this region, I'm going to change colors here because why not? Positive means I have an increasing function. So I have a positive slope, which means my function's increasing. Here, I've got a negative slope, so my function is decreasing. Here, I've got a positive slope, so my function is increasing. And here, I've got a positive slope, so my function is increasing again. So the pink tells me what my function's doing, f of x. So my function is increasing, decreasing, increasing, increasing. And at each of these parts here, it's 0. So if I see my derivative is changing from positive to negative, which means my function is changing from increasing to decreasing, if I want to draw a picture here, I should get a maximum at this point here, because I'm going from increasing to decreasing. Right here, going from decreasing to increasing, I should get a min. So I should get a minimum right there. From increasing to increasing, not sure right now. So if I'm looking for the maximum then, I'm looking for this part here. I'm looking at negative 4. So let's switch back to the other color to talk about our answer. We say f of x has a relative max at x equals -4 because f prime of x changes from positive to negative. So f prime of x changes from positive to negative, so I can prove that I have a maximum there. There were 3 different possible extrema or critical points, but I found the one that was the max and min. Cool. I also showed you here the increasing, decreasing intervals. Just remember that positive slopes mean increasing function, negative slope means decreasing function. Last example here at the front. So if I want to find the absolute max and the absolute minimum function values, I'm going to look for the local max and mins, but I also have to test the endpoints because I'm given an interval here from -4 to 2. So the first thing I need to do is I need to find the critical points that could possibly be local maxes and mins, that could also possibly be the absolute max and min. So if I take the derivative of this simple polynomial function, I get 6x squared plus 6x minus 12, and I want to set that equal to 0 to find my critical points. I'm going to divide everything by 6 to make it nicer, to get x squared plus x minus 2 equals 0, which has a nice factoring of x plus 2, x minus 1. So my critical points, or my extrema that I could possibly have, are -2 and +1. These are both in my interval from -4 to 2, so I am going to have to test all these values. So I want to find my function value at -4. So I'm going to take all these values, the critical points and the endpoints, and I'm going to put them back into my original function to see which value gives my function the highest and lowest points. So I'm plugging back into my original function here. That's what's new about this problem. So f of -4 is -28. My original function at -2 is 24. My original function at 1 is -3. And my original function at 2 is 8. Okay, so then it's asking me for the absolute max and absolute minimum value. So this is where I find my min, and this is where I find my max. So I say the absolute minimum value is -28, and that occurs at x equals -4. So the minimum value is -28. It occurs at x equals -4. My absolute maximum value is +24, +24, and that happens at x equals -2. So I can tell them my absolute max and absolute min values, and it's nice to tell them also where it occurs at. Okay, great. Let's move on. So, inflection points are coming up next. Inflection points. So a function has an inflection point when its second derivative is 0 and where the second derivative changes sign. So either changes from positive to negative or negative to positive. So inflection points, I always have to look at the second derivative. That's what's important here. Max and mins, I looked for first derivative generally. Inflection points, I need the second derivative. So if I want to find the inflection point of this function, f of x equals x to the 5th plus 5/3 x to the 4th, the first thing I do is I find my first derivative. 5x to the 4 plus that 4 comes down, 20/3 x cubed. And then I need my second derivative, which is 20x cubed plus the 3 comes down, 20x squared. And this is what I want to set equal to 0. I can factor out 20 and x squared and just get x plus 1 left over. So the possible places I could have a inflection point are at x equals 0 coming from this first piece here, or when x equals -1 coming from the second piece. I like to also set up a little -1 0 for my second derivative. And let's go ahead and see what values I plugged in. F double prime of -2, that got me -80, so this was negative. F double prime of -0.5, that was 2.5, so that gave me a positive value here. And F double prime of 1 gave me 40. This is also a positive value here. When I'm looking for inflection points, I'm looking for where my function changes sign. That's right here, where I see my second derivative change sign. So I say x equals -1 is an inflection point. Inflection point of f of x, because f double prime of x changes sign. So I get an inflection point here because my second derivative of my function changes sign. Let's just see kind of what inflection points look like. They should be pretty obvious to kind of see. If I have a graph of a function, I want to find where this graph has an inflection point at A, B, or C. Well, what I'm looking for an inflection point is where I'm changing concavity, or I'm changing from a second derivative of positive and negative. We'll get to concavity a little bit more in a second, but here's our introduction to it. So remember, concavity of the second derivative either was positive to give us a happy face, or was negative to give us a frowny face. If I have a function change concavity, I can see that's happening here at B. So if I look at B here, I can see that I have a concave down portion of my function. I'm adding this extra piece here to kind of show that if it were to keep going, that'd be a concave down function. And on this side, I'll have a concave up portion. So at B, I'm changing concavity. So I have an inflection point. I have an inflection point at B because f of x changes concavity. Changes concavity, it goes from a sad face to a happy face. A and C are pretty obviously not inflection points. They're local maxes and local mins. So A is your local min, C is your local max, B is the inflection point here. It has that kind of shape where it goes from increasing, stops for a little bit, and then starts increasing again. Let's find the intervals of concavity for this function down here. Just a reminder for concavity, function is concave up when its second derivative is positive. Function's concave down when its second derivative is negative. So if I have f prime of x, I want to find the first derivative of this and then find the second derivative. First derivative, 3x squared minus 4x. Great. Second derivative, super easy. 6x minus 4, and that's what I want to set equal to 0. 6x is equal to 4, or x is 4/6. I'm going to reduce it to 2/3. So there's really only one place where I could change concavity, right here. And I want to look at my second derivative. Let's see, if I plug in 0 to my second derivative, you get a negative value. It's -4. If you plug in 1, you get +2. Great. So here, for negative second derivative, that's concave down, or frowny face. And for positive, that's concave up, or happy face. So we can say f of x is concave up on 2/3 to infinity. And we say f of x is concave down on -infinity to 2/3. Cool. The justification here is f double prime greater than 0, f double prime less than 0. One last thing to look at, and that's the second derivative test. Okay, just a brief review of the second derivative test. Make sure I can get it in line so we can see it. Perfect. Great. So the second derivative test, this is great for tables. This is great when we're given a table or numerical table of values. So this doesn't really help us too much for algebraic. It really helps us for tables. What this tells us is if a function f of x has a local maximum at this value c, I can know that if the first derivative is 0 there, I have a critical point, and the second derivative is negative. I know local max negative seems kind of confusing. But that's because negative second derivative means I get a frowny face like this off to the side, and a frowny face has a maximum at the top. Opposite for local min, I'm looking for where my function's first derivative is 0 still, but where the second derivative is greater than 0 or positive. So I get a minimum when I have a second derivative that's positive because I get a smiley face, and at the bottom of the smiley face, I get a minimum. So why is this super helpful? If I'm given a table like this, I don't have a function differentiator, I'm given a table, and I'm looking for a relative max, the thing that I need to find a max is given to me up here. My first derivative needs to be 0, and my second derivative needs to be less than 0. So by the second derivative test, you want to look for f prime of x equals 0 and f double prime of x less than 0. Okay, let's go ahead and go back up here. Great. So where is my first derivative equal to 0? Here and here. Two possible places where I could have a local maximum. But now I'm looking for where's my second derivative less than 0, and that only occurs right here, -1. So this then happens at x equals 5. So I say f of x has a relative maximum. It's a relative maximum at x equals 5 because f prime of 5 equals 0 and f double prime of 5 is less than 0 by the second derivative test. Oop, let's move them up here. My face is in the way of the math. How sad. F of x has a relative maximum at this point, and we gotta justify by saying all this stuff here because I know the first derivative is 0, the second derivative is less than 0 by the second derivative test. Hopefully you can figure out what's going on here. At x equals 2, I have the function being 0, but the second derivative being greater than 0. You should know that that is a relative minimum there. That is a relative minimum of my function. Okay, that was a lot. There's a lot of calc to review. I encourage you to pause, rewatch the video, take notes, etc. There's a pretty fun assignment that goes with this one. All the answers can only be 0 through 9, and they can only happen once. You'll see the instructions when you get there, but there's 10 problems. Every answer is either 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, and each of those answers can occur only once. So it's a pretty fun little example problem for you to work on. Classwork, you'll submit all your answers to that on the exit ticket for today. If you've got questions, email me between 9:30 and 11:30, or come to office hours from 2:45 to 3:45. Hope to see you there. If not, I'll see you again on Friday. Have a good one, guys. Bye.